The objective of this video is to introduce the continuous conduction mode and discontinuous conduction mode of switch mode converters and analyze the critical conditions at the DCM and CCM boundary. We're going to do this by considering a buck converter, but first you'll notice that I have sketched our single pole double throw switch on the left side of the screen. I want you to pause the video and sketch the equivalent circuit for the switch. This is the equivalent circuit that we introduced in the last video. So pause the video and press play when you're ready to resume. So you should have sketched a circuit that looks like this, where we have a dependent current source on the top equal to some equivalent duty ratio, and a voltage source on the bottom equal to the same equivalent duty ratio times the throw voltage. And we previously defined this equivalent duty ratio as being dA, which is the duty ratio of our active device when we're in continuous conduction mode, and some complicated expression when we are in discontinuous conduction mode. And specifically, this case corresponded to a buck converter, where we can sketch the circuit on the left. And the duty ratio dA is the duty ratio of our active switch, whereas the duty ratio of the diode is considered to be dP, and dP is either equal to 1 minus dA for continuous conduction mode or some more complicated expression we had noted. And I want to point out here that the equivalent duty ratio being equal to dA for continuous conduction mode implies a converter where the active switch is on the top throw. If the active switch was on the bottom throw, as in a boost converter, the active duty ratio would be dA, but the equivalent duty ratio would be 1 minus dA for continuous conduction mode. So that's to say that if our converter was a boost converter, or we have an output voltage over here, this would be dA, this would be dP, and our equivalent duty ratio would be. So you have to apply the theory of the circuit in order to determine what this equivalent duty ratio will be. Alright, so now we're going to strictly consider the buck converter today. I'm going to erase our drawing of a boost converter. And I want us to start by drawing the waveforms of the converter in continuous conduction mode. So we can start by sketching Q, which is the gate signal to our active device. Q is on during the dA times T interval, and then off during the rest of the interval. When Q is on, we apply the throw voltage across the pole, and then when Q is off, our pole voltage is 0. We can next sketch our inductor voltage as being equal to Vin minus Vout, or Vt minus Vout when the MOSFET's on, and then being a negative Vout when the MOSFET's off. And the reason that this becomes a negative Vout is the fact that we have built up a current in our inductor during this interval, and that current is going to continue to flow. So during the time that our MOSFET is on, we have a current taking this path here. And when we turn our MOSFET off, that current must continue to flow, so it is going to force the diode to start conducting like this. That is, our inductor voltage will drop to whatever value is necessary to turn that diode on, following the equation that VL is equal to L di dt. And then the MOSFET turns back on, and so on. So the voltage required to turn the voltage required across the inductor to turn that diode on is a negative Vout. So the inductor has negative Vout applied across it, which lowers the voltage, the pole voltage, to 0 volts and allows the diode to conduct. This is an important point that we're going to develop a little bit more to talk about the boundary of continuous conduction mode and discontinuous conduction mode. So we can note that our inductor, the average of our inductor current is equal to our output current. And we can talk about our inductor current as having a ripple as delta IL. So then we can sketch our throw 1 current as being the current through our MOSFET, which is clearly just the same as our inductor current when the MOSFET is on, and our throw 2 current as being the current through the diode.
In summary, this was a review of the continuous conduction mode. All of the analysis that we have done so far applies to the continuous conduction mode. That is, all of our voltage and current relations and all of our duty ratio calculations have depended on operation in the continuous conduction mode.
Let's now consider something called the critical condition. And this is at the border of DCM and CCM. So last time we talked about how continuous conduction mode means that our inductor current is never zero for an interval of time, whereas in discontinuous conduction mode, our inductor current becomes zero for an interval during every switching period. And the critical condition corresponds to the point that our inductor current touches zero at the end of every switching period. So in other words, if we were to sketch our inductor current, where in this waveform we've reduced our average output current to be equal to delta IL by 2. So our average current is now half of the ripple current, which means that the minimum of our inductor current touches 0 amps. It's at 0 amps. At this point, we still say that we're in continuous conduction mode because we're not zero for any interval of time. We only have a 0 current instantaneously. However, if we were to further reduce our average output current, we would be in discontinuous conduction mode. So let's draw a graph of what that looks like. So we've now reduced our average current, so that's less than half of the ripple current. However, I want you to think about if this can actually happen. Look at the current paths that I've labeled on our buck converter circuit. And so when the trace is purple in our waveform, then we are following the purple line in the circuit up above. When the trace is red in our waveform, we're following the red line in the circuit above. So you can see that it is impossible for the red line to have a negative current. We cannot flow a negative current through a diode. So in fact,
all right, so let's
recap what's happened here. This region we've defined our critical conduction mode, which is the normal case that we've considered up to this point in the course, and we've sketched the waveforms on the left side of the screen. We talked about last time how if we were to use an active realization, if we were to replace that diode with another active switch, we would in fact avoid DCM, and we could in fact have a negative current going through our throw 2.
Let's recap what we have on the screen. We've defined the continuous conduction mode and sketched waveforms associated with it on the left side of the screen.
This is where our inductor current never goes to 0 amps for any interval of time. Next, we've considered the case where we reduce our output current until our inductor current touches 0 amps, or until there is an instant of time where our inductor current has no value. That is what is sketched here in this waveform and is called the critical conduction condition. So in the critical conduction condition, our inductor current goes between 0 amps and the ripple value. Finally, we've sketched what our first guess of the discontinuous conduction mode is down here, where we've noted that our average output current has decreased to the point where our ripple calculations tell us that the inductor current should go negative for an interval of time, which we've shaded over here. But in fact, we've noticed that our diode prevents this from happening. So instead, our inductor current just stays at 0 amps for a portion of the switching interval. And this is what discontinuous conduction mode is. Now we're going to get more into the specifics of discontinuous conduction mode in the next video, but right now I want to talk about detecting the condition of critical conduction mode and what this means for our design considerations. So we can talk about the critical inductance, resistance, or output current. Critical anything, critical inductance, critical resistance, refers to a value that results in I0, our output, our average output current, equaling half of our ripple current. So if we're talking about our critical inductance, this is the inductor value that will result in our ripple current being so large that this situation right here takes place. If we're talking about our critical resistance, we're talking about a resistor that our load resistance that's so large reduces our average output current to the point that this waveform takes place. Now, why do we care about detecting this? Well, as we previously noted, when we enter discontinuous conduction mode, our equivalent duty ratio becomes complicated. Our output voltage to input voltage relationship is no longer the simple expression that we think it is from studying the continuous conduction mode case. The second reason is that discontinuous conduction mode adds significant harmonics to our current waveform, which can cause broader interference within our system. It stresses our components within the circuit. It's in general a complicated and undesirable situation. So we want to be able to analyze our circuit and detect when we would enter the discontinuous conduction mode. And the way we do this is by studying our ripple current, which by now you should be very familiar with this expression that our ripple current is equal to 1 over inductance times the volt seconds that are applied over an interval. And we can calculate this over either this interval or this interval. And we're going to calculate it over the first interval in this case. And we can simplify this expression by noting that in the continuous conduction mode, our output voltage is equal to our active duty ratio times Vn. Alright, so we have an expression for our ripple current in terms of our inductance, our switching frequency, our input voltage, and the duty ratio of our active device. The first thing to note is that we can derive an expression for our critical output current, or critical average output current, as being delta IL by 2. And we saw this from our diagram up here. So this is very easily done as just dividing our ripple current expression by 2. So that's our critical output current. If our output current drops below this point, we enter the discontinuous conduction mode. If our average output current is above this point, we are always in the continuous conduction mode. So we can say that this is the minimum I out to avoid DCM. And we can also write this expression in terms of our output voltage by just making use of the fact that dA times Vn is our output voltage. And from here we can derive our critical resistance, which is equal to our output voltage divided by our critical conduction current, our critical output current. And using the above expression, we find that our critical resistance is this quantity, and this is the maximum resistance before we enter DCM. And finally, we can solve for our critical inductance. So in this case, we're going back to this expression right here and just writing it in terms of the inductor value L. Alright, so now we have expressions for our critical output current, our critical resistance, and our critical inductance. These are all specific to the buck converter. You can derive similar expressions for the boost and the buck boost converter, following the same process that we used here by developing expression for your ripple current and then using it to find values of average output current, resistance, and inductance when the average output current is half of the ripple current. The reason that we care about being able to detect when we are about to enter the discontinuous conduction mode is that in normal operation, our load will vary over a broad range. That means that the average load current that we expect to see will have a huge range of values. At the top end, we have some rated load current that our design spec determines. But at the low end, our load current might be a small fraction of our rated current, or it might even be 0 amps. Think about a battery charger. When you are starting to charge your battery, your power converter must supply a large DC current. However, when your battery reaches a full state of charge, you need to provide nearly no current. We've remarked that we'd like to avoid the discontinuous conduction mode if possible, but take a look at our expression for critical inductance. Our load current is in the denominator. If we really want to avoid DCM when we have no load, we need to have an infinite inductance. This is clearly not possible. We can, of course, just use a really big inductor value to minimize the operating region where we are in DCM, but that gets expensive. Higher values of inductance imply more expensive and physically larger inductors. Practical designs will place a reasonable upper limit on the inductor value. The inductor value is often chosen to suppress ripple current to a certain value, but a good rule of thumb is to ensure that the inductor is at least 3 times the critical inductor value for the rated load of a given design.